Right, starting recording. Right, that's good. Okay, let me get started. I will talk about, I will continue from the last lecture where I talked about horse race and the entropy and information. Today, I will talk about joint entropy, conditional entropy, and so on. All right, so joint entropy is defined this way. So here is the notation for definition from the left-hand side. Oh, hold on. Oh, another student's coming in. All right, so I will talk about joint entropy. And then when I use this notation, that is the notation for uh, left-hand side. I mean, definition from the left-hand side. So here, in this case, H, X, and Y, so entropy of X and Y is defined to be this. Okay, that's the message. Okay, that's the message this notation tells you. Okay, another student's coming. All right, so that's the definition. And as you can see, this is the entropy, which is the average of this guy right here, log p, y, and x. All right, so basically, like I told you in the other day, probability assignment is again a function. Okay, so random variable is a function and with the distribution. Okay, so random variable is a function with the distribution, right? Function from where to where? Sample space to the number space, right? So log p x and y is a good random variable. And then, so, if this is a random variable, say z, another student's coming. Z, then basically that is the expectation of z, okay? And then we can write z as this one right here, expectation of z, where z is defined to be log p x and y. All right, in order to represent that this is a random variable due to random variables x and y, we write this as capital letters, okay? So this expectation is due to capital X and Y, which are the two random variables. So we have to take the average based on the joint PDF, which is this one. All right, so that's the first line and the equality explained. Hold on, another question. All right, so that's the joint entropy and the conditional entropy. Conditional entropy is defined this way. Again, definition, okay, because of this sign right here, right? And that is nothing but expectation of log p y given x because of this, okay, because of that. All right, and after you have done that, then basically we can talk about this one right here. What has been changed? So it is nothing but decomposing this into px times py given x. All right, after you have done that, then basically this falls through. Okay, all right. So we know that this to that is nothing but applying the definition of joint distribution function. Okay, and after you have done that, then basically by collecting this part with this part together, right? Then we can define that as an entropy of y given x is equal to small x. Okay, so if you have done that, then we have finally have this one. Okay, so Uh, conditional entropy can be calculated this way, or you can understand this with respect to expectation, and then we can calculate with this, or calculate it with this. Okay, so multiple. Hold on, another person, another students coming in. All right. So that's clear, right? And then, oh, hold on. And then we can apply chain rule. Chain rule. Uh, joint entropy can be written as joint entropy x and y can be written as entropy of x plus entropy of y given x. Okay, and then uh, this one from the joint distribution from the primer on probability. Px and y can be written as px times py given x. Then we can do this. So first line is by definition, and the second line is by applying py given x is equal to that, right? That is equal to that. And the third line is based on log of product. Log of product is equal to sum of log. Sum of log. So these two are the same. Rest of them stay the same. And you distribute these two terms, then we got the first and the second. And then second item, when you take a look, this is argument is this one. So that is nothing but h of y given x. Okay. And when we take a look at this part, the first part, this summation over y, if you have done it first, then that is nothing but p of x. Okay, so after you have done that, then you notice that this is nothing but h of x. So joint entropy can be written this way by conditioning on x, okay, using this one. But that can be also written as py px given y as well. That can be written this way as well. And then if you apply conditioning on y, then you can write joint entropy this way as well. Okay, so joint entropy x and y. Another student coming. Hold on. Joint entropy can be written as, by conditioning on y, h of y plus h of x given y. All right, that's good, clear. If you have any question, stop me at any time. All right, now let's move on to the next chart. This is just the exercise, right? I describe this problem. Okay, so here, what is given is this PDF, or a probability mass function. Okay, given this, right? I want you to calculate h of x, h of y given x, h of x and y, and so on. And then mutual information, you have done the homework already. You are a little bit ahead of time. Okay, h of x minus h of x given y. So if you are able to calculate entropy and conditional entropies, you can calculate joint entropy, you can calculate mutual information, and so on. It's good for you to exercise this numerical example before coming to the lecture. So that's good that you have already done the numerical examples. Okay, so hold on. Okay, so this is given. Now I want you to calculate h of y. H of y, in order to calculate h of y, you need the marginal distribution for x, right? Px, you need a px. But px can be obtained from joint distribution. What do you need to do? Sum them all up for all y, for all y, right? So in this case, this is binary case, all y's. There are only two cases. So p of x, I wanted to calculate when x is equal to 0. So sum them all up, 2 over 8, 1 over 8, that is 3 over 8. And this one, 4 plus 1 is 5. So 5 over 8. So that's your distribution. 3 over 8, 5 over 8. Okay? So that's your px, right? What about py for calculating h of y? So p of y. You add this way now. Probability that y is equal to 0. You sum all x's, right? So that's 6 over 8. That is 2 over 8. Okay. That is your p of y. P of y. P of x. Okay. So once you have this, then you will be able to calculate h of x. H of x is nothing but entropy of distribution, which is p of x. So you need to write p of x right here. All right. So just by notation, right? Or you can, since this is binary, you just need one variable, one probability. That is good enough. For example, like that. So these are shorthand notations for this case. And basically, since you have binary random variable is equal to 1, if you say this is p of 0, then 1 minus p of 0 is p1. You can obtain from this equation, right? Where do you get from this? Axioms of probability, right? So you are going back to the basic fundamental, and then you can obtain it. Okay. All right, so in this class, if you specify your answer is this, then you are good. Okay, you don't have to use a calculator, but sometimes you have to use. Anyway, so that's what it is. So it is h of x. The answer is h of x. The answer is 3 over 8. That's your answer. H of y, what is the answer? Entropy over 6 over 8. That is your answer. Okay. And what about this one? Entropy of y given x. Okay. I will make use of this formula that we have driven in previous page. So in this case, I need a distribution for x is equal to small x. So in this particular case, let's say x is equal to 0. What is the py given x is equal to 0? What is this distribution? All right. That is nothing but this one. You have to take a look at this part, right? The two case, right? When this the y, right? So this one, when y is equal to 0, y is equal to 1, then that is the distribution you need to find. And in this case, what it is. So in this case, y is equal to 0. that is 2/3, right? Because that divided by this, right? And then 1/3. Okay, 1/3. So that's what you got right here for x is equal to 0. And then when x is equal to 1, now you have to do it with this part, right? So that is nothing but 4/5, 1/5 entropy of, okay? So that is x is equal to 1. That is x is equal to 0 case. All right. So once you got here, rest of them is calculator time, okay? And then once you got these three, you can calculate the joint entropy. H of x plus, which is 3/8 plus H 6/8. That is your answer. And then the unit is split. Okay, so rest of them is calculator time. All right. So that's good for this page. So we have done examples to calculate marginal entropy, H of x, H of y, conditional, and the joint. And then you can apply mutual information case as well, which we will talk about in detail in class on Monday. Okay, right. Well, h of y minus h of y to the next. We'll do this later on. All right. So once, but numerically, you just just like a machine, you can apply this formula, then you will be able to calculate. Being able to calculate will help you understand the theory later on. Okay. All right. Now the next page is this. Maximum entropy is achieved when the random variable is uniform, or maximum entropy when the distribution is uniform. Okay, so that is written this way. The same message can be conveyed with this. So entropy of x is upper bounded by log of size of the alphabet, log of size of the message set, size of the alphabet. Okay, so that's the notation that the textbook uses, right? And then here equality is achieved if and only if x is uniform over x. Okay, so that's what it is. Here, this part is easy to prove, right? When x is uniform, equality is achieved, is easy to prove. We will do it right away, right? But that part, going this way, okay? Equality only if x is uniform. That is difficult. We'll do this a little later, okay? This one later. This one, we'll do it now, okay? So let's take a look, okay? So what is the definition that random variable x is uniform over the alphabet? That is nothing but x is, let me erase this part. I will just, x is equal to small x with the probability 1 over size of x. That's the definition of uniform distribution over X, right? For any X in the alphabet, right? For any X in the alphabet, X is equal to X with the probability 1 over size of the alphabet, right? This is same as this language, uniform over X, right? So apply this to entropy. H of X, entropy is this, right? And that one, this part can be written as P of X is also this, right? So apply that one right here. And then note there is a minus sign. Bring that minus sign inside. That is going to be 1 over X. Then this part falls down to the size of the messages. And then rest of them is sum over all X. Alright, since this is constant, you can bring it outside. Then sum of px is 1, so that is nothing but size of the message cell. I forgot the log, right? So we have proved this part. Okay? Yeah. And then this part is also true, but we will prove it later on. Okay? And then here, now, when we take a look at this one, half proved for the equality part. If it is non-uniform distributed, then the random variable, entropy of that random variable is not maximized. Okay? All right. And this is true for all random variables, right? But in the case of additional constraint, for example, let's suppose that there is a constraint on the variance, right? Variance is equal to 1, right? And then what is going to be the entropy, maximum entropy? Well, what type of random variable will maximize the entropy? In such a case, the answer becomes Gaussian. Okay? In that case, we will talk about this later on in the second half of the lecture. The second half of the class. Okay. So in that case, Gaussian maximizes. It is called a differential entropy because it's a continuous random variable. Gaussian maximizes entropy under average energy constraint. Average energy here means second moment, okay, with zero mean, right? So that's the case that we will talk about later on. But for now, for discrete random variable, this is always true, okay? Always true. And then equality if and only if X is uniform. So for now, discrete cases, you just need to remember this, okay? Maximum entropy when uniform. Now, here, in order to attack the more difficult proof, which is this part, only if part, so we have to consider what is a convex function, and then the Jensen's inequality, and so on, right? I will talk about this in greater detail on Monday. Let me briefly go through a little bit today. So there is a definition of a convex function. Convex function is just like this one, right? Convex, right? If you have any 2 point, x1, x2, and then here fx1, fx2. And basically anywhere in this point between x1 and x2, you can define it as lambda x1 plus 1 minus lambda x2, right? Then where lambda is belonging to this interval, right? Then you are talking about x in this interval between x1 and x2. And then if you select that one, now you can talk about, so this we can say average of x. We can say average x, okay? Average x. Then we can talk about function of average of x anywhere in this point. So that means, for example, if we choose the right here at the half, where lambda is equal to half, that means it is right here. And then this point. Now we can talk about function of average. Function of average, then we are doing this. Okay? That is function of average. Function of average x. Okay. And then if we draw a chord right here, and that is right there, here in this part is, what is that? Average of function. So that is average of function, right? And if it is convex this way, as you can see, that is always going that way, right? Or equal. Where do you have equality? Right here. When lambda is equal to 1 or minus 1, equal. Or function, convex function is defined this way. Sometimes it is strictly convex. Sometimes you have some linear, interval as well. For example, here, if you have a convex function like right here, here is a linear interval. In such a case, equality is met. So that is the definition of a convex function. And basically, function of average is less than or equal to average of function. Average of function of average. The inequality goes this way. All right, that's it. And then there is a strict convex case. Function is always, there is no linear part in it, right? Always going like that. Second derivative, if it is differentiable, is always is greater than 0. That is that case. In the strict sense case, then we say this is in general true, right? And then equality is true. Equality is not allowed, basically. Okay. Right. So that's the strict convex function f, right? In such a case, in order to not fall into the fallacy, we have to exclude this interval. Lambda is excluding the last point, 0 and the 1. Okay, the endpoint. Endpoint has to be excluded in order to have this. Okay, that's it, right? And that is this condition right here. And then there is a strictly convex case. And then if it is differentiable, then if you take the derivative twice, that should be greater than or equal to 0. Okay, then f is convex. All right, so that's the definition of a convex function. And then with the drawing, more careful one. but this one is more intuitive, very quick, right? And one of the examples of a convex function is what? Y is equal to x squared, or fx is equal to x squared. That is a convex, strictly convex, okay? And case, and what about the convex case? Y is equal to x, or f of x is equal to absolute value of x. So goes something like that, right? Or x. So in this case, this is convex function. There's a linear part in it. All right, so that's that. And applying that to Jensen's inequality, for any convex f, now you understand what we mean by convex function. For any convex f on a convex set U, you can just ignore this convex set part. You can just understand that part. We are doing this, average x, okay? And then when lambda is equal to half, like we have done the drawing, then we can talk about the function of average and the average of function. Average of function, here is function of average, right? So that is this part, that one is this part. So you can always remember convex U, then inequality goes this way, right? As you have seen in this picture. Then basically we apply this for any lambda, and we can generalize it with the probability distribution P1, P2. And then once you are able to do this, then you can do for P1, P2, P3, and so on and so on. Okay. All right. So that's the Jensen's inequality. So average of a function of average, f is convex, then inequality goes this way. And with the equality for strictly convex f, that is the if and only if x is a almost sure constant. What do we mean by this? So that is nothing but x is a constant. So since probability distribution is an assignment that you design, so we can design this way. So for example, x is equal to 1. This one with the probability 1. Or any other value. Let's say 2, 3, 4, all the others with the probability 0. You can design x is equal to 1, so effectively it is a constant because no probability is assigned to any other value of x, right? You can define constant this way. So that is what we mean by almost sure constant. Okay? So if it is almost sure constant, that part is easy. That part is a little bit difficult, but if we have applied the strict convex function f, it falls through immediately. All right. Okay, that's the Jensen's inequality. So from now on, I want you to remember this part, okay? That is the part that we need to utilize in information theory class. We need to apply this. And then convex U, concave, this is concave, this is convex. So if you remember convex U, then you can recall this result and utilize it. Now we can move on to relative entropy is non-negative. So we want to see why this is true. So relative entropy is a measure between two distributions, P and Q. All right, P and Q. And then its name is sometimes this, pullback labeler divergence. So KL divergence, relative entropy, they're the same language, okay, in this class. And then that is nothing but measure between two distributions, PZ, QZ, okay. So by definition, that is D, P, and Q. And that is defined to be sum of PZ, log PZ over QZ. And then this Z right here, dummy variable for that one is over SP. SP is the alphabet for distribution P. Okay, alphabet for distribution P. Okay. All right, just that, and SQ is alphabet for distribution Q. And then this one says strictly positive distribution, no zero probability masses. So here we are talking about, let's say, alphabet Z running from, here is Z, maybe 0, 1, 2, and then SP is these three numbers, PZ equal to 0, PZ equal to 1, PZ equal to 2. Sum of these three numbers should be equal to 1, right? And another one is so that is the Q equal to Z, okay? So these two numbers in general are different, right? So for example, here is 0.1, 0.5, 0.4, here maybe 0.2, 0.3, 0.4, 0.4, like that. So this in general are not equal, right? In sometimes these support set, here in this case, the support set 0, 1, 2, here 0, 1, 2 are the same. But sometimes, SQ might have a different support set as well. So 1, 2, 3, and then 0.2 here, 0.4 here, 0.4 here, right? There's another SQ with a different support set. The entropy are the same, but the support sets are different. So in this case, that is the examples of, these languages that we introduce right here. Okay, and then we don't want to include a zero probability message here. So we can, that is something that we can include some other support set, let's say 3, 4, 5. Oh, sorry. Oh, all right. With the probability assignment zeros, right? We don't want such things, okay? In this definition. Then we can talk about relative entropy defined this way, which is the distance between the two distribution PZ and QZ is non-negative. that can be proven this way. So I will maybe cover this part for today. Rest of them I will cover next time. Okay. So here, applying this definition, and then I have a minus D between P and Q. And then since I have a minus sign, then the inside the loop, it should be inverted. So QZ is the QZ appears upstairs, right? Okay, so that's just by applying the definition of DPZ at DPQ, and then that should be that is upper bounded by log of this. Okay, so why is that? So what is this? This log of argument and log of argument right here. So this is average of function, which is log, right? And then that is function of average. And then by applying the Jensen's inequality, basically we can have a function of average. This is concave, log is concave. So function of average is higher than average of functions in this case. So that is from Jensen's inequality. And then from here, we can cancel out PZ. Then this is nothing but log of sum of QZ, but with respect to support set of SP. Okay. And the SP and SQ might be different as we have seen in these cases. So that one is upper bounded by log of sum of QZ. Okay. And this one I have changed into SQ, right? Instead of SP. All right. Then that one, sum of the distribution should be equal to 1. So that is equal to 0. Okay. All right.
교수님,
Yeah.
끊어서 죄송한데요. 조분함인데요. 혹시 그 줌에 못 들어간 학생이 있어가지고 혹시 봐주실 수 있을까요?
예, 줌에 못 들어. 지금 내가 이 수업에 열중하다 보니까. 그래.
죄송합니다.
감사합니다. 몰랐네. 모두 수락. 어차피 녹음을 할 거니까. So I am recording this, so there will be no problem. Okay. So once you have done that, then basically we can show that the relative entropy is so applying the negative sign. So this negative relative entropy is always smaller than equal to 0. Multiplying both sides with a negative sign, then we come to this conclusion, right? And the equality depend only if PZ equal to QZ for all Z, okay? All right. So since this is important, we will prove this multiple different ways. So hold on to it, okay? So for now, relative entropy is non-negative. I want you to remember that part. Okay, hold on. And rest of them are some calculations, sample calculations. Basically, relative entropy is non-symmetric. If you have a P first, and if you have a P later, this calculation will lead to differences in general, right? Because it is PZ log PG over QZ, right? Sum of Z, right? Versus sum of Z. If you Q have appears first, then we are talking about this. So in general, they are different. They are different. Right, relative entropy is not symmetric. And then there are some examples when this parameter, when we parameterize the distribution P with R, so we are talking about binary, right? And Q with the parameter S, then basically that is the result for relative entropy P and Q. And that is the result for relative entropy for Q and P, right? So these are all these are all functions of R and S, okay, as you can see. And then if R is equal to S, if R is equal to S, they are the same distribution. Then the distance between the two distribution shall be equal to 0. As you can see, it is actually so, right? Because log of 1 is 0. Log of 1 is 0. Okay, so it is 0. And case 2, numerical example, when R is half, S is quarter. And then calculation. As you can see, they are different in general. So you can take a look at some of these examples. And then here is another approach that relative entropy is non-negative, right? Hold on. Again, suppose PZ and QZ are strict positive, right? No zero probability masses, same as before, right? And then if relative entropy is 0, then PZ has to be equal to QZ for all S. Can we prove this? That was the difficult part, right? The easy part is when PZ is equal to QZ, when PZ equal to QZ, then this is 1. Then log of 1 is 0. And 0 multiplied with the 1 is equal to 0. So going this way, if so P equal to Q, then D is equal to 0 is easy. This is easy, right? But going this other way, right? Only if part, right? If D is equal to 0, then P should be equal to Q for all Z. That is the difficult part, right? So that's the difficult part, right? So we have to use a Jensen's inequality, whatever technique that we need, come up with, we have to use it, okay, for this part, okay? Difficult in general, all right? So we will talk about that. For now, let's take a look, okay? Sum of PZ, log PZ over QZ. That's nothing but dPQ, right? And then I have upper bound going this way, and the sum of PZ, 1 minus QZ over PX. What am I doing here? Where is this inequality coming from? That's the question, okay? You have to ask a question, right? So that is nothing but, let's take a look at this, log of x, okay? That is this, right? Log of x. And then that is different from this part. So what is that? 1 minus x inverse, isn't it? Because this is inverted, okay? Top and bottom switched, okay? So that is this, right? And then Maybe we are talking about this one, right? That's the question. Is it? Right? Then, okay, then you need to think about that one. There's x, 0. Since we are dealing with the log, so x should be non-negative. And I have this 1 over x. 1 over x graph is this, right? And then minus. So minus is this. Step up this by 1. So that's 1 minus 1 over x. Where is this crossing? When x is equal to 1, 1 minus 1 over 1 is 1 minus 1. So that should be equal to 0. So here is 1. And then this one says, that is 1 minus 1 over x. And then I have log x. Log x. If I draw log x, log x. That is log x. All right. So if you draw these two curves and compare, aha, this is true. This is a yes, right? And then equality is achieved when x is equal to 1. Okay. Right. So that's the inequality right here. It is due to this inequality. And then equality achieved if and only if x is equal to 1. Yeah. Then after you have done that, then basically rest of them is easy. Then sum of PZ, because of 1, sum of PZ times QZ over PZ, right? So PZ cancels out. That is sum of QZ, the rate of pi. And this summation in the beginning is over the set of SP, right? So I have, that's why I have SP. I have SP right here. And then that is greater than or equal to 1. When PZ is exactly equal to QZ, it is 1 minus 1, it is equal to 0. When they are different, sum of PZ is always greater than sum of QZ, because this is the support set of P, right? So that's what we got right here. And then that's it. We have proved it again. The relative entropy is non-negative. Equality if and only if P is equal to Q. So that's what we have. All right. And then we can apply this result, and then we can prove this statement. Entropy is maximum when uniform distributed. We have proved this part, but we, reference to the later part of the lecture for the only if part, right? Only if part, right? Only if part was difficult. Now we have tools to prove it, prove the only if part, right? And let's do it, okay? Let Ux be uniform on X. You know what I mean by that now. So H of P is equal to that, and then that one is right here. I add and subtract the same thing, where Ux is a uniform distributed random variable. I mean distribution of the uniform random variable X. Okay. And if I tell you the detail, that should be over the alphabet of X, right? Okay, once you have done that, then basically by combining the first term, combining this one with that first, I have a minus. I'm combining that one with the last one, sorry. Last one, minus sum px log ux, right? And the plus, now these two terms, if I combine these two, sum of log is log of product, right? So ux over px, okay? So over ux over px. I'm good, right? So here, what is this? Ux is uniform. So that is nothing but entropy of random variable u, random variable x, right? So I think I should say, I have said random variable u, right? Random variable. So that is the entropy of random variable u, which is uniform distributed. So that is the log of size of the alphabet. Okay. What about this one now? Okay, this part is px ux inverse, right? So I can bring the, so I have log. So I can bring the negative sign outside. So that is that. So replace this with this. Then I have minus relative entropy, right? Px appears at the top. So that is the p and u. And then I have a negative sign. So I have minus here. So once you have this, okay, so that's the result so far. So that is h of p, and that is equal to that. And since d of this part is non-negative, right? This h of p is this constant minus non-negative number. So h of p is maximum if this part is equal to 0. So that's the proof of entropy of maximum when uniform distributed, right? So that part is 0 means relative entropy is 0 means P is uniform distributed, okay? P is uniform distributed, all right. Okay, so that equality is met if and only if Px is equal to Ux, such that when P is uniform. So I think I'm done proving. So if you have any question, let me know. And then once you have done that, basically relative entropy is non-negative. You have proved twice. And then you can apply that to mutual information. So here mutual information, here is definition. Definition can be written this way. So this is averaging over all x and y here. And then here is the argument. That argument can be written as this. Okay. So this is the expectation over distribution of p, x, and y of this argument, this random variable. Okay. And that can be also written as relative distance between two distribution, which is joint and product distribution. Joint and product distribution. Okay. And Since this is relative entropy, that is non-negative, so I can write this way. So mutual information is non-negative. Equality is met if and only if product distribution is equal to the joint distribution, right? If and only if Pxy is equal to Px times Py. Okay, sorry, Py. So this is what? In another language, that is, I mean, for all x and y, right? That is x and y independent. So if x and y independent, mutual information is equal to 0. Okay? If x and y is not independent, then this measure is greater than 0. That is the message that we get. Okay? So, and rest of them, not very difficult. Okay? So we will continue this next time. So I'm done with today's lecture. Okay? And like I told you, I have done recording of this. After I have ended this Zoom session, I will upload this to the recorded video to the YouTube and then class webpage. Okay? And on Monday, I will have a in-class meeting. Okay? That's it for today. If you don't have any question, let me stop here. Okay? No question? Thank you for joining. See you next Monday. Okay. Oh, there is someone. Thank you. Okay. All right. That's it for today. Bye-bye.
선생님, 혹시 들리시나요?